So in this video, I'm going to be talking about function orthogonality. Function orthogonality. And you might say, what on earth is this weird sounding abstract mathematical term, and why would we care about using it? Well, the answer is that equations like Schrödinger's equation, which we're going to be dealing with a lot in the following videos, and we can just write the time-independent equation here, but also equations like Maxwell's equations and other partial differential equations that show up all over the place in engineering and mathematics, so other partial differential equations. These are often absurdly difficult to attack front on. So we don't just want to attack them directly. We don't want to try and find a solution. Often we just want to use properties of the solutions without knowing anything about what the actual solutions are. So for example, without knowing anything about what psi of x actually is, the wave function, we can use properties of that wave function that are due to the underlying equation that make our lives much, much easier and make a lot of otherwise impossible problems possible. And I would argue that function orthogonality, this guy right here, is probably the most powerful of all properties in mathematics that we use to attack differential equations like the Schrödinger equation, Maxwell's equations, and others. It's actually one of the things that underlies things like the Fourier series and the transform, as well as things like polynomials. This concept, function orthogonality, is what gives these constructs their power. And so in this video, I'm going to be describing just what it is, what do we mean when we say function orthogonality, how do we test for it, and how do we use it. So if you've taken linear algebra, and I hope you have at this point, because it'll make this video considerably easier, we know that vectors can be orthogonal. So we can take, and we can test for that orthogonality by taking the dot product. So let's say we've got some vector A, which we can represent as a column vector as 1, 0, and B, which is some vector, say 0, 5, for example. And if we take their dot product, we know this is just the pointwise multiple element multiplication. So 1 times 0 plus 0 times 5. And this is equal to 0. So these two functions are orthogonal. So anytime the dot product is 0, anytime the dot product of two vectors is 0, this means the functions are orthogonal. Or sorry, the vectors are orthogonal. See, I'm getting ahead of myself. And so I'd really like to figure out some sort of test like this dot product to figure out whether two functions are orthogonal. And this will also be sort of our definition of what it means for two functions to be orthogonal. So say I've got two different functions, sine of x and sine of 2x, for example. And I want to know if these two functions are orthogonal. Well, the easiest way in my mind to do this is we can use our understanding of vectors to try and define orthogonality for functions. So if we graph sine of x and sine of 2x, we know sine of x is going to look something like this. Let's just draw it over a single period. So let's say that this is x equals 0. This is going to be x equals pi and 2 pi. And if we draw sine of 2x, we know that in the same distance, x goes from 0 to 2 pi, we're going to have 2 periods now instead of just 1. So this is going to be 2 pi, or x is equal to 2 pi. So this is our x-axis. 0, this is going to be pi over 2. This is going to be pi, and this is going to be 3 pi over 2. And both of these functions go from 1 to -1. So they're just your garden variety sine waves. We deal with them all the time, especially in electrical engineering. So let's just redraw this is sine of x, and this is sine of 2x. And so how do we think of these functions? Like, how would we define a dot product between these two functions? We might say, Jordan, that idea is ridiculous. Dot products only exist for vectors, but just bear with me for a minute. Could we represent these functions, so this function sine of x, this function sine of 2x, could we represent these as vectors? And we might just say, well, yeah, let's just try it out, just for fun. Let's, instead of taking the whole function, let's just take the function every pi over 8, for example. So let's take like 8 values of this function from 0 to pi, and then 8 more from 0 to 2 pi. And that's a vector, right? So we're just taking the function's values and putting them in a table, or a one-dimensional table. So for the value of x is equal to 0, that corresponds to sine of x being equal to 0, or the first column or the first row in the vector being 0. If we had pi over 8, that would be what? I am staring at a table right now, 0.38. Similarly, 2 pi over 8, we'd have the value 0.71. That's just pi over 4. 3 pi over 8, we'd have the value 0.92. 4 pi over 8, or pi over 2, we just have the value of 1. And you might imagine we can continue doing this on and on and on, and we can form a vector of this function. So we can just tabulate its values. And you might say, well, Jordan, why'd you choose values of pi over 8? Clearly that's extremely arbitrary. And yeah, you're totally right. I could have chosen pi over 5 or pi over 10. But really, if it's a function, we don't want to choose points from this function. We want all values of this function. So ideally, we'd like these entries in our vector to be super finely spaced. So maybe delta x is, we want this to approach 0. We want this to be as close to 0 as possible. But for representing the function as a vector, this is sort of the general idea. We're taking points of this function, so 0, pi over 8, 2 pi over 8, so on, and just representing them as a vector. And we can do exactly the same thing for sine of 2x. So we can calculate its value for x is equal to 0. That's also 0. For pi over 8, that's 0.71. For 2 pi over 8, that's just 1. 3 pi over 8, that's a 0.71 again. And then 4 pi over 8 or pi over 2, that's just 0. And so we've got a vector. This is a vector for sine of 2x. And we've got a vector for sine of x. And so you might imagine we could just take the dot product of these two vectors. So we just do pointwise multiplication of all the values, and then we add them up. So 0 times 0 plus 0.38 times 0.71, and so on and so on. And if you do this for a full period of sine of x, or sine of 2x for that matter, you'll get that this sum is actually equal to 0. And that's really interesting and kind of suggestive, because this is how we're going to define the dot product, or as it's often called, the inner product between two functions. We just take the values at each point of the two functions and multiply them by each other, and then take a sum over all the values. Or if we want these values to be even more finely spaced, so instead of pi over 8, maybe we want I don't know, pi over 16 or pi over 32, or maybe we want them infinitely spaced, so we want the distance between these two to approach 0, then this sum will just start to look a whole lot like an integral. And so we're going to be taking the integral of these two functions with respect to x. And in our case, it was from 0 to 2 pi, for example, but you might imagine going from any value to any other value. And if this integral is equal to 0, then these two functions are said to be orthogonal. So if we've got any two functions in any region, so let's call it f1 of x and f2 of x, and some region from a to b, if their integral over that region is equal to 0, then f1 and f2 are orthogonal. And the way that we test for orthogonality is we take the two functions' dot product, or you can think of it as an infinite vector, so an infinite dimensional vector multiplied pointwise multiplied by another infinite dimensional vector, and then the values are summed up, and that's just an integral. So if this dot product is equal to 0, then the two functions are orthogonal. Now, where this becomes really useful, is if we know ahead of time the functions are orthogonal. So we can use some theorems or some tricks to figure out that two functions are orthogonal. Then we know that their integral over that region is equal to 0. And this might not seem to be super useful at first, but this property will actually allow us to deal much more easily with the Schrödinger equation, because often we don't want to deal with f1 and f2 directly. We'd like to set as many things equal to 0 as possible before even starting any computation. And this property, function orthogonality, is what's going to allow us to do that. So I hope you enjoyed the video. If you did, please give it a like and subscribe to my channel. If you're feeling particularly generous, you can always donate to my Patreon page. If you have any questions or comments, please feel free to post them down below, and I'll see you next time. Thanks for watching.